One last example of solving a linear differential equation, y prime plus y cos x equals cos x. Now, this is actually going to be one of the easiest ones that we solve as long as we do all of our techniques correctly. So, first thing we're going to do, it's already written in the linear form. The differential's isolated. We have y times a function of x is equal to a function of x. So, let's define p of x to be equal to cosine of x, and q of x, which is on the right-hand side, is also cos of x. So we can't go wrong. The integration factor I is e to the integral of cos x dx, or e to the sine x. All right, and initially, that might look like it's going to be a really nasty sort of function to work with. However, it's actually going to make the integration very nice for us. Our formula, y equals 1 over I, so that's 1 over e sine x, times the quantity of the integral of q of x, which is cos x, e to the sine x dx, plus c. Our goal now is to be able to evaluate the integral. And this integral, although it looks like it's pretty nasty, and we certainly could do this by parts, we'd end up with one of those iterated integrals and it wouldn't be nice to be able to evaluate. It's much more suited for a u substitution, because if we look at the composite function, e to the sine x, the derivative of sine is exactly cosine, and we'd end up with something really nice with this. So let's go ahead and use a u sub. U is going to be sine of x, du is cos x dx, and that's exactly what we want. So we're going to now rewrite this integral, y equals 1 over e to the sine x. The integral is going to be e to the u du, all right? And e to the u, remember sine x is u, and then cos x dx is du, plus c. Antiderivative of e to the u is e to the u, so we have y equals 1 over e to the sine x, e to the u plus c. We're going to back substitute, remembering that u is sine of x, so y equals 1 over e to the sine x times e to the sine x plus c. And now we can see that this very, very nicely works out. If we were to distribute 1 over sine x, all right, it would cancel the first term out, and we would just end up with 1 plus c over e to the sine x. All right, now again, just like every other problem, that's our general solution. However, we need the particular solution. So for our particular solution, we go back up. Y at 0 is 3, so we're going to end up with 3 equals 1 plus c over e sine of 0. Sine of 0 is 0, e to the 0 is 1, so that just cancels out. We subtract 1 from both sides, and we get that 2 is equal to c. We substitute back in, and we're done with this one. So y equals 1 plus 2 over e raised to the sine x. That's our particular solution. Again, if you don't trust your solution, or maybe you do trust, but you just want to go through and verify it, use Desmos, plot it in Desmos, along with the slope field. All right, so that's the last of our linear types of equations that we're going to look at least for now. We are going to look at a second type of differential in this series, and that's going to be called an exact equation. Exact equations are pretty easy as well. Exact equations are set equal to 0, and you have a function of xy times dx, a function of xy times dy. If you were to take the partial derivatives of this m with respect to y and this n with respect to x, and they equal one another, that is an exact equation. So we're going to test first. We're going to find some partials. And then if it is exact, then what we're going to do is we are going to integrate m with respect to x. We're going to take that derivative with respect to y, and then we're going to solve for some unknown function g of y. All right. Now, if it's not exact, that means we have to go back, see if it's linear. If it's not linear, we have to see if it's separable. So as you can see, as we start getting more and more techniques under our belts, the problems become a little bit more difficult to decipher. All right. Although the algebra and the calculus might not be too bad. Let's just take a look at a really basic equation. Okay. So we're going to have this 2xy dx plus x squared plus x squared 3y squared quantity dy. That should be equal to 0. So let me go ahead and set that equal to 0. On yours, it'll probably say that. On mine, maybe I just deleted it by accident. And we have this y at 1 is equal to 2. We're going to define m to be the coefficient of dx. So that's 2xy. We're going to define n to be the coefficient of dy, x squared 3y squared. And we're going to take each of the partial derivatives with respect to y and with respect to x. So the partial of m with respect to y. So we just think of 2x as a constant. The derivative of y is 1, so that's going to be 2x times 1, otherwise known as 2x. All right, so we're going to hold on to that. We are now going to take the partial of n with respect to x. All right. We're going to treat anything with a y like a constant. The derivative of x squared is 2x. The derivative of 3y squared is 0 with respect to x. So that equals 2x. And I want you to notice that the partials are indeed equal to one another, so it is exact. Now, unfortunately, what that means is you have to keep going with the problem in the exact method. Okay, so if we're going back up here to the steps, that's step 1. Test to determine if the differential is indeed exact, which we just did. Step 2 is easy. We are going to differ or integrate 2xy with respect to x. And we're not going to worry about the constant of integration, and I'll show you at the end of the problem why we don't worry about it. Now think of y as a constant, so just pull the y out front. If you've never done multiple variable integration, just think of it like a constant. And we know the antiderivative of 2x is x squared. So what we're going to get, and here's where we have to be careful, we are going to get x squared y, not plus c, but some function g of y. And you might be thinking, well, why not plus c? Well, g of y could be a constant, right? But let's say g of y was equal to sine y cubed for some reason. Well, if you take the derivative of g with respect to x, that's just 0. So in other words, if we took the derivative of the antiderivative g of y with respect to x, g of y would go away every single time. So that's why we have a function. It's because of the multivariable integration. All right. So that's step 2. You're always going to have g of y every single time you're done. Now step 3 is we are going to take the partial of this answer. Okay, so we're going to take the partial with respect to y of x squared y plus g of y. Right? And that's going to be equal to, now remember, x is a coefficient in this case, so the derivative of y is 1, so that's going to be x squared times 1. We don't know what g of y is, but when we find its derivative with respect to y, it's just going to be g prime of y. All right. Now, we are going to set that equal because this is an exact equation. There's some function that when we take the partial, it's going to be equal to this part right here. Right? And so we're going to take and set this equal to n, which was x squared plus, I believe it was 3y squared. All right. For those of you that have taken Calculus 3, you might remember seeing this towards the end of the course in conservative vector fields. This is really just some function phi, and this is our function phi sub y. Okay, so anybody that's seen this before as an exact equation, or I'm sorry, a conservative vector field, this is similar to what's going on with this. All right, now to finish this off, notice on both sides we have an x squared, so they cancel out, which means that g prime of y is equal to 3y squared. To get rid of a derivative, we're going to integrate both sides with respect to y, and that means that g of y is going to be equal to 3y cubed over 3, or y cubed. Right? And that's what we needed to finish this problem off, because this is the solution, except we needed that unknown function g of y. All right? So our phi, which is technically going to be the function in terms of xy, is going to be equal to this x squared y plus y cubed. All right? So that's our function. Now, how do we know if that's even close to right? Well, let's take the partials. Okay, so I'm going to take f sub x, which is the partial with respect to x, and I'm going to take the partial f sub y of the function up top. Okay, so if I take the derivative of this with respect to x, that's 2xy, and then y cubed goes to 0. If I take the derivative with respect to y, the derivative of our x squared, I'm sorry, or just derivative of y is just going to be x squared as a coefficient. Derivative of y cubed is 3y squared. Now remember these. We have 2xy, x squared, 3y squared. If we go back up, look at the original function. We have 2xy, and then we have x squared, 3y squared. And that's what it means to be an exact differential equation. There's an unknown function that when you take the partial with respect to x, the partial with respect to y, it gives you the coefficients of x and y, of dx and dy respectively. Now the last thing we have to do is we just have to solve the initial value part of it, and that's pretty easy. Right? Because fxy is really your constant. So all you're going to do, okay, so this is our general implicit solution. We'll just call it general. Right? To get the particular solution, we're going to find f, and I forgot the values already, at -1, 2. And that's going to be equal to -1 squared times 2 plus 2 cubed, which should be 10. So that means that for our particular solution, this constant is not just fxy anymore, it's 10. So we get 10 is going to be equal to this x squared y plus y cubed. And that is the particular solution. Unfortunately, we can't get an explicit solution for this because we can't solve this for y. All we can do is just keep it in the implicit form, and that's okay. Not every time are we going to be able to get an exact solution for an exact equation, all right? But we can just keep it in that implicit form and we'll be good. So a suggestion might be, before we start moving on to other exact equations, review this video, take a look at some of the processes that we use to be able to solve and also to check the solution. And then we'll work through about 2 or 3 more of these so that way you can have multiple examples to base your studies upon.